All right. In this problem, we will have the interest periods smaller than the payment periods. Now imagine the situation. You have a savings account and the interest in the savings account compounds on a monthly basis. However, the payments that you can do, for example, deposits or withdrawals that you can do in this account are quarterly. Okay, so the payments are on quarterly basis and the interest periods are smaller than the payment periods, which means between consecutive cash flows, there will be compounding more than once. So you see, it says when the interest periods are smaller than the payment periods, the interest may be compounded several times between payments. Now, how can we solve this problem? Now, the best way is to find the effective interest rate for the payment periods. Okay, so you see, because the payments are made less frequently than the interest periods, we need to calculate the effective interest rate between the payment periods. So how do we do that? Let's just say alpha is the number of interest periods in each payment period. In the previous example that I have given to you, if your payments are made on quarterly basis, or in other words, in every 3 months, and if the compounding occurs on monthly basis, in that case, alpha is just going to be 3 because there will be 3 interest periods between each payment. Then how would you calculate the effective interest rate per payment period? So you see, R over M, again, nominal interest rate divided by the number of interest periods per year will give you the effective interest rate for each compounding period. However, because the interest periods are, the payment periods are greater than the interest period, longer than the interest periods, in that case, we need to calculate the compound amount factor that corresponds to each payment period. You see, this effective interest rate, R over M, will be compounded alpha times between each payment period. Therefore, the compound amount factor for a payment period will be 1 plus R over M to the power alpha. And since this is the compound amount factor, if we subtract 1 from that, then you are going to get the effective interest rate in each payment period. Okay? And how many payment periods we will have in the investment horizon? You see, M times N was the number of compounding periods in a year, or in the investment horizon, sorry, N is the number of years, M is the number of compounding periods in a year. Therefore, in the total investment horizon, there will be M times N compoundings. And when you divide this to alpha, you will get the number of payment periods. Okay. Basically, you are calculating the effective interest rate in each payment period, and the rest will be proceeded by assuming the interest periods and payment periods are coinciding. Because when you calculate the effective interest rate per payment period, this effective interest rate will be the effective interest rate of the payment periods, and the rest is the same as the previous problem. Now let's practice this in question 5. It says for a savings account, if the nominal interest rate is 6% and the interest compounds monthly, what is the effective interest rate for 6-month period? So in this question, actually, our objective is to calculate the effective interest rate just by using this formula. Okay, nothing more. So this is not a problem related to a cash flow diagram or a engineering economics analysis. Basically, we are just trying to calculate the effective interest rate in a 6-month period. Now, your nominal interest rate is 6%, and the interest compounds monthly. Therefore, there is an effective interest rate that corresponds to each month, which is 6 divided by 12, right? So the effective interest rate in each month is 0.5% or 0.005 as decimal. Now, the question asks us the effective interest rate for each 6-month period. Now, we will assume that the payment or payment periods are on half a year or semi-annual basis, which means alpha is equal to 6. So the payment periods are 6 months, and the number of interest periods occur between each payment is just going to be assumed as 6. Now this means in order to calculate the effective interest rate for 6 months, first you calculate the effective interest rate for per month. So this is R over M. And 1 plus R over M is going to be the compound amount factor in a single month. In 6 months, there will be 6 compoundings. Therefore, if we take the power of 6 of this factor, you are going to get the 6-month compound amount factor. And if you subtract 1 from that, you would get the rest as 3.04%, which will be the effective interest rate for 6 months. So this is how you calculate the effective interest rate for your payment periods. Now in this question, we can practice it a little further. This time we are actually going to solve a question related to this situation. You see, it says an engineer deposits $1,000 at every quarter to a savings account that pays interest at a rate of 6% per year, compounding monthly. So the input of the question is given in this whole sentence. So we need to understand. There is a uniform series of payments at a constant amount, which is $1,000, but at every quarter, which means the payment periods are every 3 months. Every quarter means every 3 months we have the payment periods. To a savings account that pays interest at a rate of 6% per year, compounding monthly. So in this account, we have a monthly compounding logic. However, the interest rate is given in yearly terms, which is the nominal interest rate, and the monthly effective interest rate is just going to be 6 divided by 12. However, in this problem, the payments are made quarterly. The payments are made quarterly. Therefore, in this problem, we actually need to calculate the effective interest rate for each quarter. Okay? So not just the monthly effective interest rate, we should be further calculating the quarterly effective interest rate. This is going to be calculated first. Then we can answer the rest of the question. How much money accumulates in the end of 5 years? Now, these quarterly payments are just going to continue for 5 years. So this means because in every year we have 4 quarters, in 5 years there will be 20 quarters of payments of $1,000. So actually we are trying to solve a question of a uniform series that will continue for 20 periods, where the periods are quarters. And the question is, what would be the future value accumulated in this account? First of all, we need to determine the quarterly effective interest rate. Now, unfortunately, it is not equal to 6 divided by 4. First, you need to calculate the monthly effective interest rate because compounding occurs monthly. So it is just going to be 1 plus 0.06 divided by 12. Remember, this is the monthly effective interest rate. And then you multiply, you take the power to 3 for this monthly effective compound amount factor to calculate the quarterly compound amount factor. When you subtract 1 from that, you would get the 3-month effective interest rate or quarterly effective interest rate as decimal, of course, and the percentage representation is 1.51%. So you see it is not exactly 6 divided by 4. Now you get the quarterly effective interest rate. Now, how many quarters do we have in 5 years? So 5 times M is 12. We have 60 months divided by 3. We will have 20 payment periods in this problem. So this means for 20 payment periods, we are going to deposit an installment of size $1,000. And in each quarter, the effective interest rate is 1.51%. And there will be 20 quarters in this problem. How much money will accumulate in the account in the end will be calculated by multiplying the installment size with the uniform series compound amount factor under the 3 months effective interest rate, 1.51%, and the number of quarters in our investment horizon, which is 20. Now, of course, since we do not have any page that corresponds to such an interest rate in our compound interest tables, and it may not be a very good idea to apply interpolation at this point because, I mean, this value is very, very close to 1.15 anyway. So it is best to use the exact formula for the uniform series compound amount factor, which will be equal to, in that case, which will make the future value equal to $23,146. Okay, if you just calculate this compound amount factor. And this is how we calculate or solve a problem when the interest periods are smaller than the payment periods. The whole trick is to determine the effective interest rate for the payment periods. And the rest is the same as in the previous question when the interest periods coincide with payment periods. But first, you need to determine the effective interest rate for the payment period. Now, in the next problem, we are just going to solve the opposite situation. In this problem, the interest periods are going to be larger than the payment periods, and we are going to solve this problem in the next video.